start again from this script. So I will try to go quickly through the few arguments that are remaining. And well, yesterday I've been asked, how do we do post-hoc for repeated measures ANOVA? It's not very difficult. It's of course it's not easy in the sense that you can use the easy package. You have to do a little bit more job. For example, what if we want to do within subject ANOVA using the ANT data that we saw yesterday, the attention network task data? First thing that the easy package did for us and that we now need to do manually is calculating the means. So if you remember, we had this attention network test data in which we had reaction times as a dependent variable, and then a flanker and that could have different levels, and a Q that could also have different levels. The data were perfectly balanced, so we don't need to care so much about how we take the average of those reaction times. But how do we... oh, and there were, of course, many trials for each subject in each Q and flanker condition. So we need first to take the raw reaction times and the average of those reaction times within each condition defined by the combination of flanker and Q. So this is not very difficult if we use dplyr. What is this code? I create a new data set, it's called ANT collapsed, and I am summarizing, so taking the average reaction time and calling a new variable in a new data set, again reaction time, RT. But first I grouped the data according to the subject identifier, the flanker, and the Q. And that just, there are of course other methods to do that in R, like I think there is a function that is aggregate, but I typically use this syntax. So let's quickly do it. Okay. So just load some packages, go here.
From mixed ANOVA or from repeated measures?
This is repeated measures, but for mixed ANOVA you just easy because you need to add additional between subject variables, but that's straightforward, so no particular issue. So let's load the data ANT. Then we create ANT collapsed. I don't know if you can see it. How do you do that zooming?
Windows plus.
Windows plus. That's it.
Works, it works. Interesting.
Extremely helpful. Okay.
Yes.
So ANT collapsed. No, sure. No.
You have to move.
Ah.
You can move on your screen.
Oh yes.
Ah, but it's you're duplicating the screen, not extending.
Oh yeah. Okay, but that's cool. So ANT collapsed. So group by ANT, and we have subnum. Oops. Subnum. Blank Q. And then we pipe the grouped thing into summarize of and we have reaction times equal mean reaction time. Oh, lowercase. I think it should be okay. Let's see if we have some output here. So up. Now we have this. So for each individual, we have the average reaction time in each combination of flanker and Q condition. The second thing we need to do, okay, stop. Okay, is that we now need to specify the ANOVA model, the AUV model. You remember in the easy package, besides doing all these collapsing internally, it also returned the AUV output. If we check that option, return AUV. Well, that's because AUV is the function in vanilla R that performs ANOVA. For having post-hoc test, the best way is probably to just specify the ANOVA model in AUV manually, and that will be similar to regression. So we have the reaction times are predicted by the flanker and the Q, But then we need to specify using this syntax that I found a little bit confusing, honestly, but how the error are organized, so they are decomposed. So you have that in subnum, then this symbol, and we have that the main effect of flanker of Q and their interaction. That's what the multiplication symbol means in the formula syntax. So main effects and interaction are essentially are repeated measures variable within the subject number. So each individual is observed, I mean, each level of this variable and their combination are observed in each individual. And then the data set that we want to use, that in this case is the collapsed data set. So if we do that, okay, if we do that, come on, okay, so let's, okay, fit equal to AUV, and we have reaction times predicted by flank multiplied by Q, and then what was it? Subnum by Q data collapsed. Come on, let's. Okay, it has its pros, this lens, but also its cons because it cannot see my screen. So, okay. Where's the output? No. Maybe here. Okay. So I did clearly something wrong.
It didn't run though.
It didn't run because I maybe misplaced a parenthesis. No, what's the problem? Oh shit, that's it. It's not a comma here, but a plus. So I need to, it's like in mixed models, I need to put a plus here. That's it. Now I have the output of my ANOVA, for which I can ask a summary. And I see the results here. So that I have the main effect, significant main effect of flanker in the F-test associated of Q, and the interaction between the two. Now I have the IOV object, and okay. Now that I have the AOV object, I can ask for post-hoc. I need to use the package emmeans, it's called. Now we need to load it. So include it in this call. Now we use function emmeans. The fitted object, and then we need to specify these specs, which means we are telling our which post-hoc for which factor or factors we need a post-hoc. In this case, for example, the main effect of flanker. And if we do this, we get the estimated marginal means. But if we want also the post-hoc, the function is pair, and we pairs, and we get the post-hoc test comparing all the levels of the variable flanker. And here we see that the Take method has been used for adjustment automatically. We can ask different methods for, I think I don't remember the argument if it's p-adjust or adjust. For example, you can ask adjust Bonferroni, and I obtain Bonferroni corrected p-values, etc. We can specify essentially any correction that is supported by R as adjust. So maybe let's make it bigger. Okay. Also, we can, instead of flanker, of course, we can ask for the, okay, we can ask for the main effect of Q, or we can also ask for the interaction between the two. So flank Q. For example, this is the post-hoc for the interaction effects. So we see all the combination of levels of flanker and of Q compared with all other combination of flanker and Q, and the associated p-values. So of course, we have many of those significant because it's simulated data and in perfect conditions. So this is what you need if you want. I mean, I'm sure that there are other options to simplify things in R as well, so packages that do that automatically for you, facilitate things. But I decided that at some point, if you really want to unleash the full power of R, that the best thing is to just use the embedded function AOV, and then the output of that is supported by most other functions to do post-hoc or other kinds of analysis. Any questions? I also wanted to show very quickly the assumption test for the general linear model. So this is, something that is not always done after, for example, regression or an ANOVA, because I wanted to show you that because unlike other things, like post-hoc for repeated measures ANOVA, that's incredibly easy to check. So imagine that we do let's do a multiple regression. In this case, we use the data Boston. Let's open the dataset Boston, which is in package mass. So you need to put mass in your payload code. Let's open data Boston. Then we run a regression. We run a regression such that the median value of the houses is predicted by, we put just a dot here after the tilde symbol. And the dot means include all other variables in the data frame as predictors. And then we specify that the data set is Boston, and we save the fitted object to something we can call again fit.
This is a bit too fast and too small.
Oh, sorry. Yep. So, what did we do? This line opens the dataset Boston. It's important that the package path has been uploaded. And then we run a regression using the usual formula syntax, medv tilde. Medv is the median value of the houses in Boston in the 60s, 70s. And instead of specifying all the predictors manually, if you put a dot, it's just telling R, put everything left in the data frame as predictor. So it's like running a regression, specify manually all the variables separated by a plus. We now have a fitted object. If we do summary of the fitted object, we see this. So we see that the criminal rate predicts a decrease of the value of the houses. The zone, I don't remember what is this, but industrial is something regarding the land, positively predict the value. Industrialization, not so much. The fact that Chas is the river, and the presence of the river increases the value of the houses, etc., etc. So, that's it. But what if we want to check assumptions? So, for example, the homoscedasticity, the linearity, and the normality of the distribution of errors. Well, it's very easy because we need just to write plot of the fitted object. this will produce this thing that we see below. Hit return to see the next plot. So what we need to do is just enlarge our plotting area and hit the enter button. And we will be shown a series of plots that allow us to evaluate the assumption underlying the general linear model. So this is a fitted versus residuals plot. So we can check for homocelasticity. We can also, so homocelasticity meaning that the assumption that the variance of error is constant across different levels of the predicted values. In this case, short of, but we see something different that has to do probably with the non-linearity of the relationship. So we see that the predicted values of the dependent variables still will be able to predict the residuals, meaning that there is most likely a non-linear relationship here. So if we can predict the residuals, so what we do not predict in the regression, from the predicted values, that means that there is very likely to be a non-linear relationship involved. If we hit return again, we see the QQ plot. This allows us to evaluate the normality of the distribution of the residuals. And here we see a huge deviation here. There's some deviations here, but here something extremely deviating from what it would be expected. So if you have normality, you should have all these points on a straight line. And these are the theoretical quantiles of the distribution of errors assuming normality, and these are the observed. These would be the standardized what we would expect in terms of standardized values according to the quantiles of the residual, and these are the observed ones. And if you see such deviation, means that they're probably not very normally distributed.
Those are the outliers.
Oh, yes, those guys are those cities are outliers, meaning that, but yeah, also this, and some of those are marked automatically with the labels. I am not sure why only these guys are labeled, but these are also not maybe because they are above 4 standard deviation or something in terms of zeta scores. So if you again hit return, you see this, which is a similar plot as the first one, except that now it's a square root of the standardized residuals on the y-axis, and this one is to find outliers actually in regression. So this is the leverage versus standardized residuals. The leverage is a measure of how much an observation is influential in changing the result of the regression, and the residual means how bad are we in predicting that observation. So if you have this contour plot is the Cox distance, and if you have observations here, means that they are really dangerous outliers, because they are both observations that weigh a lot in our regression and observation that we are very badly predicting. So that will be, for example, when you have a straight line, that will be a point here that changes really a lot the position of the regression line, but is very far away from what we can predict with a linear regression.
Sorry,
Yep.
Is there a way to have an help to read these graphs? Now you told us that the line is the Cox value. So is there a way to get an help on how the graph is?
Let me see, because I think if we go on, yes. So okay, this is not very straightforward. I mean, we need to enter a little bit in the logic of R. So the function lot if you only ask for the help of the function plot, you will see, okay, this kind of stuff. So the default scatter plotting function is not very useful, or generic XY plotting. This is what we are using. So the idea is that plot is a generic function, meaning that it does different things according to what it gets in input. So if you do plot, for example, of two variables, you get a scatter plot. But that's not what's happening here. To ask R, give me the help file for the plotting method for linear models. The idea is to ask for plot.lm. .lm means that give me the plotting function for the object of class linear model. If you do that, you get the help plot diagnostic for an LM object, and here you have an help. 6 plots are currently available: residual gain fit, scale location, blah blah blah, and the plot of Cook's distance. By default, the first 3 and 5 are provided. Here you have other options that you can specify, the arguments that you can describe them in more detail, and then here you have the details. So scale location plot is this, the QQ, etc., etc. This is the help file. Also here you have in the help files also the references, so that you can have more information. So yes, you can, but it's not very straightforward, because you need to realize that what you're using is not the scatter plotting function, but a method applied to the object of class linear model. I also put some descriptions here on the slides, so that tell you what everything is and how it should be interpreted. Of course, but this is not very relevant to me. But you can also export the residuals. So there is a function. So let's call it residuals of the fitted object. You export all the residuals to a variable. Then, for example, you can run a histogram of this. Here you see the residuals. This is just another way to represent the same thing that we already seen. You can also let me check. I always misspell this. Yes, I never know how to put the H here. But then you can run normality tests, NHST normality test on the residuals. I think that the QQ plot is a more principled way, because of course these are the fact that you have a significant deviation from normality is also dependent of the size of your sample. So, but if you want, you can also report. I mean, the point is the function residuals. Maybe let's make this bigger. Allow you to export the residuals to another variable and use them as any variable. So you can plot them or run tests on them, anything. And that's it. But I will say this, compared to other things that you can do in R, is very easy, because you just need to, the most basic, I mean, not very basic stuff actually, quite advanced I will say, you get them all using just plot around the fitted object. Any questions? What time is it? Let me see if we have some more. Not that much. So, okay. So I put here something about interaction, multiplicative effects, and about mediation. So about interaction, here maybe I will just leave that in the slide for a moment, and you can look it up if you're interested. But I tried to check for packages that do make interaction analysis easier, and one is this pequod package, in which you have this lmres function, because that essentially is similar to linear model function, except it's called lmres. You do a multiple regression with interaction effect. It has an embedded centering option, so you can tell R center for me these variables, And the main advantage is that so essentially you don't need to center them manually in the formula. But the main advantage is this, that you can take, I'm going through that quickly because I don't want to stay too much on this, that you have a function here, it's called, what, give me, no, okay, why?
Windows minus.
Windows minus.
Lost.
Windows minus. Okay. No. I got lost. Okay. I mean, I don't know if you can read it. I don't think so, honestly. But there is a function. It's called simple slope that does simple slope analysis. You need to specify the fitted object, which variable you want to use as a predictor and which one as a moderator. It's very straightforward, actually. And you get the simple slope analysis. So the slope when the moderator is at -1 standard deviation and +1 standard deviation. And you can also plot that using this plot slope function and get the simple slope analysis. So, I mean, it's not, in terms of programming, it's very straightforward, and you can get simple slope analysis for a simple interaction effect. But what I wanted to show maybe is the mediation. That's why, that's because this afternoon I will show you a little bit about the power analysis for mediation models. So maybe it's better if I show you how to do mediation first. And there is this function called mediate in the package psych that is also very straightforward. It has also moderation interaction effects, but I think that pequod function works better for that. So the function is called mediate, and you decide which is the dependent variable, which is the independent variable, this like in the formula syntax, plus, and you can add mediator, one or I think also two mediators or more, using this syntax. So simply add them, but with wrapped in parentheses. And then the rest is the same as a linear model. So let's try this. Let me see. Also using the Boston data, mediate, add, tilde, I don't remember, maybe I'll start, I used start, and plus age, data equal to Boston. So that's quite similar to the linear model function, but if I run that, I get something else in the output. So I get this nice output, visual output, so that I get the total effect, the direct effect, and the two paths on the mediation model. So from the predictor to the mediator, and from the mediator to the dependent variable. And here, Windows minus. If I do summary of the fitted object, I also get all the regressions from which these values are taken. So I get the multiple regression in which the predictor and mediator both predict a dependent variable. So I get p-values, etc. Standard error, t-test, and p-value. I get also information regarding this regression here. No, I'm sorry. That was that x and y. No, this is this regression. I get information regarding this regression here, and also this one. But finally, I get let's make it bigger. Eventually, I get this. So this is an estimate of the indirect effect of LSTAT, the predictor, on the dependent variable mediated by the age of the houses. I get the observed indirect effect the average of the bootstrapped indirect effect and the lower and upper confidence interval, bootstrap confidence interval, which is something very close to what process does in SPSS. So this, I assume that you are familiar with the mediation analysis, but the idea is that you cannot evaluate run an NHST test on the mediated effect, because you cannot assume that the sampling population of the mediated effect is normally distributed. And that's because you typically assume that the sampling distribution of the two paths, like each regression coefficient, in this case will be this one and this one, are normally distributed. So, but you're now taking the product of these two, and the product of two normally distributed things is not normally distributed. So this using an NHST test will not be will violate the assumption, the underlying assumption that Daniele discussed earlier. And for this reason, you typically want to use a bootstrap procedure, and this is the output of that bootstrap procedure. In this case, I would say that the effect is we could say it's positive, but not. It has 0 in its confidence interval. Now you can also you also have other options, of course, in the mediate function. For example, you can ask standardized coefficients, regression coefficients. I think you can also set number of iteration for the bootstrapping. So you could, I don't remember which one is the default. So mediate and iter. What is it? Come on iter.
It's 5,000.
Okay, it is. Come on. It's 5,000.
I think so.
Okay, 5,000. Yeah, you can increase it to 10,000, for example, and rerun the analysis. Now it takes a little bit more. And when it's done, here we see the same analysis, but now we have the standardized regression coefficient and standardized mediated effect. And now this is again the confidence interval with the 0 in the lowest boundary and 12 in the upper boundary.
Don't we need to set a seed here if we do bootstrapping?
So we do bootstrapping if we want. So the idea, as Daniele discussed earlier, if we want to get exactly the same result every time that we run this analysis, or on different computer in different situations, we can just set a random seed generator like this. I typically use the value 1. And here we run the analysis, and now the results are reproducible. But of course, if you run the analysis, and each time you run the analysis you get a very different confidence interval, instead of setting the seed, increase the number of iterations, because otherwise you get stuck in you may get stuck in the illusion that that is your confidence interval. Instead, it may be an imprecise estimate.
So what happens on each iteration?
So what it's doing is it is sampling with replacement a number of observations that is as large as the total number of observations, and is simply redoing these regressions again. It's multiplying these two coefficients, and it's saving the value. And it does that over and over and over and over.
You say it does all the observations every time?
It samples, but with replacement. So if you have 100 observations, it takes 100 observations, but some of them will be repeated.
Okay.
So that's the idea. Which I think is the same thing that process in SPSS does. Okay, this is just to show you that you can get beta coefficients. I also had something about Manova. I don't know if we have time, but maybe
10 minutes.
10 minutes is enough. to give you the last the last hit with the Manova, Mancova. I mean, that's not it's not very complex. The only thing is that you need, it's just a variation on the theme of regression analysis, essentially. But there is, just to inform you, there is a Manova function with lowercase m in R, which is the default function in R to do the Manova without installing any other package. But there is a better function called capital M Manova in the car package. Yeah, it's annoying. Yeah, but because I don't know how, I don't know why, but they at some point they decide that in R you only have by default type 1 sum of squares, and maybe they just don't care. Maybe they just say it's yeah.
It's fine.
Yeah, no, I think that yes, you can implement it yourself, or maybe they think it just. I mean, if you look at the regression coefficient, you don't need any type of sum of squares. So it's you look at the regression coefficient and do it yourself. I have no idea, but then. All these packages, the possibility to extend everything and personalize it is what makes R great. So people in car package implemented this Manova with a capital M that allow you to get type 2 and type 3 sum of squares. So how do you do Manova? I don't think that I have the time to show you that direct by coding. It's easier maybe if we look at the slide for a moment. But the syntax is not that complex. So it's just a linear model, but instead of having a single dependent variable here, you want to specify cbind, so binding of the columns of many dependent variables. Then tilde, and then the usual list of independent variables separated by the plus symbol or the multiplication symbol or whatever you want. So the formula syntax, as usual. The only difference here is that you have cbind of many dependent variables. Then you specify the data set from which you want to take those independent and dependent variables. Now you use the Manova function around the fitted object, so you save the output of RM. Instead of doing summary, for example, you ask for a Manova. And then you save this to another object, a variable or something. You can call whatever you want. I call it out. And as you ask for the summary of this object, and if you ask for univariate equal to true, you also get the ANOVAs for each dependent variable separately. And that's it. That's Manova in R. So I know that, I mean, if you're very unfamiliar with R, we introduced many variations on the theme, but it's just somehow straightforward extension of the linear model. And you need only to use this Manova and summary on the Manova object. Unlike what happens in the easy package, the covariates, if you have any, they are treated as continuous predictor though, like in a regression. Not as they're not partialed out beforehand. So, okay, this was an exercise that you. I'm just going to the solution here. The idea was predict the. Yes, we want to regress the three SCL scales. These are psychopathology scales that scores that I made up on the gender of the participant, and these are three dependent variables. So, and you want to get a Manova summary of results. So you load the packages, reader to open the data, dplyr to manipulate, and car to have the Manova. Import the BPD data. Do this. So a linear model in which the independent variables are three, and they are binded as a matrix essentially, and they are predicted only by sex. You run this Manova and you ask the summary, and you don't get the output because I didn't put it in the slides, so I will just copy paste this code in here and run it, and this is what we get. So okay. So we get multivariate tests, and we have different options for, in this case they are all equal because we only have a dichotomous predictor, but they can be slightly different. They are what you get, I think, also in SPSS. So the P-late trace, the Weeks lambda, Hotelling-Lowry index, and the Roy, I don't remember what this is exactly, but they essentially all converging tell you that there is no such effect of sex on the psychopathology variables, and you get a p-value. And here you will get also, where is it? The univariate tests, you should get them, yes, here. So you get the F test, the F for the three dependent variables, and the p-values for the three dependent variables separately. So these are essentially the three p-values if you run three separate ANOVA. And what if you want, okay, here the example, yes?
Do you need to take care that dependent variables are on the same scale before, or does it do it for you?
No, you need to take care of that. You need to take care of that. That's a good point. So if you want, maybe you can standardize them beforehand or doing something like that, yes. And if you want, you can add covariates, and they will be treated as predictors in a regression and not partial doubt. So this is just the same thing, but we added another continuous predictor, the borderline personality disorder checklist. These are just made up data. They're not real data. And the syntax is the same, except that you now get also a continuous predictor. So I won't show that to you now because I think we are out of time. Yes, 3 minutes. Just what I need. But what if you want to use the easy approach to covariates? So no, that's not very complex, because you can run first analysis, first linear model, in which you take the dependent variable predicted by the continuous covariate, you save it, and to an object you can call fit1. You take the residuals, and that's your independent variable, your dependent variable. So if you take the residuals of this regression with the common residuals that we saw before, you get the residuals of the three dependent variables once you partial out the borderline personality disorder checklist, and you can run a Manova on this object. And then you get, a Manova in which the covariates are treated as if you were in the easy package, so that you can have consistent univariate test with easy as well. If you really want to do that, it's not that complicated. Okay, this is also okay. And for the moment, that will be it. I just skimmed very quickly through these topics, but do you have any questions regarding the general linear model so far? Then I think you're free to go to the coffee break. Thank you very much for your attention.